Hello to everyone who's watching this video. My name is Hao Zheng. I'm currently a PhD student in the University of Pennsylvania School of Design. My research topic is mainly about machine learning and its application in architectural design. I'm glad here to present our current research paper, Machine Learning Assisted Urban Filling. Generative Adversarial Network, GAN, is a model framework in machine learning that is designed to learn and generate image data. In GAN, a network generation candidate is generated, and then the discriminating network evaluates it. The game is organized by data distribution. Typically, the generated network learning maps from the potential space to the data distribution of interest, and the discriminating network distinguishes the candidates generated by the generator from the real data distribution. The training goal of the generator is to increase the error rate of the discriminator, for example, to deceive the discriminator by generating new candidates that the discriminator considers real, while the goal of the discriminator is to increase the error of the generator. In architecture design, the design process usually follows certain criteria arranging objects inside space. Previously, we applied a GAN to train and predict architectural image data in pairs from the color label to the plan drawings. In this case, we firstly define the color label, which actually contains the design information of the primal layout. Then the neural network learn to generate the patterns of the furniture under the guidance of the color label. In another paper, a partner for plan generation via generative adversarial networks in this conference, GAN successfully learned and generate a partner for plans only based on the design boundaries. The quality and the unity of the patterns in the training images directly influence the resolution of the generated images. The frequent cooperation between the human designer and the machine designer will result in a future that the computer will not add but also decide the design. Besides architecture design, urban design is another widely discussed domain that highly depends on the image-based data. Therefore, in the age of artificial intelligence, we propose a machine learning method to teach the computer to provide the urban design drawings in the early design stage, releasing the heavy load from the urban designer. GAN supports learning and generation of the images of urban design plans. The final goal of this research is to build a tool that takes images showing the site conditions of a city as input and outputs images showing the urban design plans. In urban design, city maps are usually presented as color images for simplification, in which different colors represent various elements in the maps. In this research, 5 colors were selected to represent those elements. That is, red corresponds to the road, green to the green land, blue to the river, white to the building, and black to the empty space. These 5 colors, as well as their corresponding design elements, can represent most of the situations in urban design tasks. To train the networks, a dataset of different cities' maps were collected. 8 cities were selected and classified into 4 tiers, in which the first tier cities contains Beijing, Shanghai, and Shenzhen. Then the second tier cities are Chengdu, Fuzhou, and Guiyang. For the third tier city and fourth tier city, Kunming and Kaifeng were selected. Those 8 cities can represent the typical urban design projects in China with different scales. The input data contains the required information to start the urban design project. That is, the elements of roads, greenlands, and rivers. And the output data reveals the design contents of the project. That is, the design building as well as the environment. Last, the images of the required information and the images containing buildings of the cities are fed into the machine learning neural network separately. Also, the large map of the whole city is divided into small samples of 256 pixels times 256 pixels, while matching the data structure of GAN. Taking the training of Beijing city map as an example, this figure shows the training loss of the generator and discriminator. During the training process, the generator and the discriminator compete with each other to improve the performance. Therefore, the convergence of the loss value shows the fact that the generator and discriminator are evolving with each other to retrieve a smaller value while being treated by the other to obtain the larger loss value. Thus, the training is successful. After training, the neural networks can be used to generate new maps of the city based on the input images. Based on the results, the original input images are firstly be fed into the neural networks, then the generated images are compared with the original output images to evaluate the similarity. If the generated images show a great similarity to the original output images, the urban planning styles can be evaluated as characteristic, which is easy to learn. For instance, from the set of the maps by evaluating Fuzhou City, the generated images are similar to the original image of the city. Thus, it can be concluded that the urban planning style of Fuzhou City is well learned by the system, which means the training data has high accuracy. From the perspective of urban planning, this result reveals that the design strategies in Fuzhou City are simpler, more uniform. However, in another case, by evaluating the city maps of Beijing City, the generated images of the city have comparatively less similarity with the original ones. For example, the generated buildings and the real buildings in the areas with yellow box marked are very different. The differences exceeds the acceptable range. Therefore, the urban planning style of Beijing City is not well manifested on the generated image. Thus, it can be concluded that the learning result has low accuracy and the design strategy of the city in different areas are more different in larger cities, for example, Beijing. Along the process, cross validation is also utilized for the evaluation. Firstly, trained by eight different groups of city maps, 8 models representing 8 cities are obtained. Then by fitting all input images of the 8 cities to the 8 models, 64 groups of output images are generated, representing the predicted urban design solutions based on the corresponding input site conditions and the trained general models. This figure shows the selected result of the cross-validation experiment. 4 cities from each tile, Shanghai, Chengdu, Kunming, and Kaifeng, are selected, and their cross-validation results show the generated urban planning solutions by machine learning with different design scales. For example, the generated plans using the site conditions of Chengdu and the models of Shanghai can be regarded as the urban planning solutions with the design strategies from Shanghai, but in the areas of Chengdu. In this way, it's easier to tell the distinction between the original and generated images, which is concluded as testing data accuracy. Also, the urban planning style of 4 tiles is shown on the generated map, which can be compared to the original urban texture of the style imaging to rule out the accuracy. In detail, according to the result, the design strategy in each city are different. The models in the first or second tier cities always generate a large number of buildings. For example, in figure D1 and D2, the generated urban planning images are unable to be understood, since the road system is very loose in the fourth tier city. It's hardly seen in the dataset of the first or second tier cities. Thus, the model performs badly. The model trained by the city images of the third and fourth tier cities always generate fewer buildings. For example, the generated images in figure A3 and A4 are very different than the ground truth image in figure A1. The building areas are far less than the real situation. Therefore, the most different design strategies in urban design in China is the number of buildings that each city will have. By comparing figure A1, A2, A3, and A4, we can see that the buildings generated by the Shanghai model and the Kaifeng model are placed more related to the road system, while the buildings generated by Chengdu model and Kunming model are placed more independently. By comparing figure C1, C2, C3, and C4, the buildings in the Kunming model and Kaifeng model are larger as fewer single units, while the buildings in Shanghai model and Chengdu model are more separated as smaller units. This phenomenon reveals the specific design strategies of each city based on the urban planning data. In conclusion, by comparing the generated images of city maps of the original counterparts, the two sets of images can inspire the urban researchers with different or similar urban planning styles. By constantly learning the images of all kinds of cities, Yue Ren is capable for conducting urban design. In addition, the generative analysis based on the generated results with different models and the same site conditions provides a method to evaluate urban design and conclude the design strategies under the same circumstances, which is impossible by the previous traditional analytical methods. Thank you for listening. That's it.